Welcome back to part 3 of our Godot Masterclass. In our last video, we built a working coin collector prototype and learned how to communicate using signals and autoloads. But building a small prototype is one thing. Keeping a growing code base under control across dozens of scenes and systems is something entirely different. The way you structure your Godot project from the beginning directly affects how quickly you can make changes, how easily you can debug issues, and how confidently you can add new features later on. Today, we're going to clean up our sandbox. You're going to learn industry standard folder structure, naming conventions, how to extract logic into reusable components, how to manage dependencies, and finally, how to bulletproof your project using Git version control. Let's scale up. Now, just like we did in the beginning video, it's tempting to create folders just by asset type, a single folder for all scripts and another for all scenes. But as your game grows, it becomes incredibly difficult to find what you need. Instead, it's far more practical to group things also by their function. In our example, we have here our scenes and our scripts folder, so our asset sorting, and then sorted by function in their respective folders. All the characters, so the player and the enemy, are in the characters scenes folder. All the levels scenes are in the levels scenes folder. All our collectible scripts are in the collectible scripts folder. And all our systems are in the systems scripts folder. Doing this disconnects the code from a massive global folder and groups related things together, making it easier to reference. Now, let's talk about naming. Consistency is everything. A standard rule is to use something called Pascal case. Pascal case is used for scenes, classes, and scripts. If we look at an example here, such as our level manager script, we see it's in Pascal case with a capital letter at the beginning of each new word. For raw asset files, such as these background images, background underscore clouds, background underscore color underscore desert, this naming convention is called snake case and is more widely accepted naming convention for files like this, the raw assets you're going to use for your game. By doing this, you can tell at a glance what kind of file you are working with. It's also highly recommended to document your naming conventions in a single document structure or a README file in your project root, so future collaborators can understand your layout instantly. You can create this file by right-clicking in your file system. In this case, I'm going to click on my resources folder, hover over create new, and go down to text file. I'm going to name it readme.md, and then we can add our notes here and then save it. And now your readme file is right here inside of your resources folder. If you want to build a scalable game, each script should manage one thing. Your player script should only be concerned with controlling the player, like handling movement and input. It should not be calling UI methods, saving scores, or managing enemy logic. This keeps things easy to read and debug. To help with this, we must avoid hard-coding absolute node paths. If you use a hard-coded path to find your score label and then move that UI node later, your game will fail. Another trap is circular dependencies. A circular dependency happens when two systems rely on each other directly, like script A calling a function in script B, while script B tries to call script A. This makes codes fragile and prone to breaking. Don't let systems directly talk to each other's scripts. Instead, route communication through signals or external scripts. One common pattern is for both systems to talk to a neutral controller. Let's look at our wave controller or wave manager for an example of this. This acts as a hub to collect data, update the game state, and decide what spawns next. We see here our variables, the enemies to spawn, and keep track of enemies defeated. So the hub function decides what happens when an enemy is defeated. We have here enemies defeated plus equals 1. It will print the total number of enemies defeated in our output, and then if the enemies defeated is greater than the enemies to spawn, then it's going to start the next wave. When the wave is completed, it's going to print wave complete, spawning the next wave here in the output. It's going to reset the counter of enemies defeated. It's going to tell how many enemies here to spawn. When multiple nodes share behavior, you shouldn't repeat the same code in each script. Instead, we design our systems as reusable components. Components are focused, independent scripts or nodes that can be attached to any scene. A health system is a perfect candidate for this because it's needed across players, enemies, and destructible objects. Instead of rewriting health logic over and over again, we can create one health GD script that extends node. The script doesn't assume anything about the node it is attached to. It simply manages health value and emits a signal when health reaches 0. We can now attach this script as a child node to our player scene, as in our example here, and in our enemy scene. This type of component-based design makes debugging far simpler. If you want to add invisibility frames later, you'll only have to modify the health GD script once. Let's separate our data from our code using custom resources. Godot supports external resource files that end in .tres or .res, letting you store data outside of scripts and scenes. This is extremely helpful when you want designers to tweak values without touching code. We can create an enemy stats script that extends a resource and give it an export of variables for the health and speed. Then right in the editor, we can create a new tres file based on this resource. This lets you define many enemies with unique stats using the exact same script and scene simply by assigning different .tres files into the inspector. In our example here, our enemy script exports a stats variable called enemy stats. When we click on our enemy, we'll see this stats folder appear. We have a goblins stats.tres file that we can then drag into our stats folder, and the stats from our goblin.tres, if I open this up, you'll see it's 100, 150, and damage 10. If we go to our enemy, it reflects the same information from the goblin.tres file. You can apply this same flexibility to your scenes by building template scenes which are designed to be instanced at runtime or reused in multiple parent scenes. To make these templates incredibly powerful, you can use the @tool keyword at the top of your script. A script marked with @tool runs even inside the editor, allowing you to preview animations, update positions, or use the _draw function to visually display boundaries while designing your levels. Finally, let's talk about the ultimate safety net, version control. Version control protects your project from mistakes, whether they are your own or someone else's. The most reliable system for this is Git. Now, a real common misconception is that Git and GitHub are the same thing. They aren't. Git is the actual software running locally on your computer, tracking your files. GitHub is just a cloud website where you can back up those files later. You do not need the internet or a GitHub account to protect your project right now. To start tracking your local files, open your terminal and make sure that you are in your exact Godot project directory. For me, that's here in our Godot intro path of our projects folder. I'm going to double click in here, and I'm really just going to type in cmd, press enter. This will open up the command terminal inside of our project. I'm going to type in git init to initialize the git, and it's going to create a git repository in our project folder. You'll know it's done that because you'll see this hidden .git folder appear. From there, in your Godot file, project, you can right click in your resources, go to create a new text file, and simply name it .getignore.txt. Don't forget this dot in the beginning of the name. In this folder, you're going to type in all the files you don't want to be backed up as history. In this case, junk files like our imports, .tmps, .log files are going to be ignored so that they don't bloat our history. With that saved, let's lock in our first official save state. Going back to our terminal, we can just type in git add period and press enter. This stages all our scenes, scripts, and tres files. Then from there we can type in git commit m initial project setup. Now let's say you want to experiment with a new mechanic, but you're terrified of breaking your game. You can branch your project by typing git checkout b This creates a safe parallel version of your game. You can test your changes here, and if something goes wrong with your player's double jump, you can simply discard the branch and your main game is perfectly untouched. Later on, if you do want to back this up to the cloud or collaborate with a team, that is when GitHub comes in. You would simply grab the remote link from GitHub and then type git remote add origin, and then you'd include the website github.com, your username, and then simply your game projects file name inside of GitHub. After you do that, then you're going to simply just type in git push u origin main. As your game reaches major milestones like a playable prototype, you can even tag stable releases locally by typing in something like git tag version 0.1. This acts as a permanent stamp on a known working build, meaning no matter what happens, you can always check out that tag and restore your game to perfect working order. Use signals, autoloads, and exported scenes to create flexible links between parts of your project. Avoid hard-coded references and circular callbacks that lock your logic in place. And always use version control. Once you start treating your project like a living code base rather than just a folder full of experiments, you will feel drastically more confident adding new features and fixing bugs. If this video helped you organize your project, leave a like and hit subscribe. In video 4, we're tackling GD script essentials and the math that drives game engines. I'll see you there.